So today is lecture 3, and I'll start a little bit from before we left off. So I'll start with the definition that I already gave of a coset. Okay, so this is a very, very important definition. So, and suppose that we have a group G, and G has, a subgroup H. It doesn't have to be like a proper subgroup. It can be an improper subgroup as well, but you know. And so for definiteness, because I want you to get the idea, let G and of course H be discrete and finite. Okay. So the idea is that for the coset construction to work, these are actually not necessary. So, these are the discreteness and the finiteness of the group is actually not necessary. And so a lot of the construction that we will do will essentially go through for continuous groups. So my aim here is to build up the intuition for finite groups, and then when you go to infinite groups, it'll be easier. Okay, so now let H say H is a subgroup, right? So it'll have some elements like H1, H2, ... say Hm. So the order of H is M, right? And one of these, it's E is contained in this set. Because if E was not contained, then H would not be a subgroup, right? Okay, now let G be some element, small g be some element in big G. And then we define the coset of H, with respect to the element small g in G as G times, it's actually, I think it's the left coset. I sometimes get those things confused, but it doesn't matter very much. So the left coset is the set which consists of that element G multiplying all the element of H. Okay? So this is called the coset, the left coset. So we want to make some comments about this. The comment is, what if you pick G to be from the subgroup H? So then you can very easily show that since G, H is H of H, and H is a subgroup, that is, it's a group, that means that, if you take H1, H times H1, H times H2, ... H times, H times Hm, because it's a group, all that it's going to do is it's going to shuffle around the elements, right? And we know that for sets, ordering doesn't matter anyway. So as a set, it doesn't change. Right? Is it clear why it doesn't change as a set? What is the group property that allows us to conclude that?
Yes, sir. The element H and capital H is inside the capital H.
Yeah, but what group property allows us to write this equality?
Multiplication.
No, yeah, multiplication, but the equality is between this set and this set. Which property of multiplication allows us to do that?
Closure.
Closure, yeah. Because of closure, so we see that if we pick G to be H, then essentially we just get the subset back. So to get a, yeah.
How do we know that we'll get all the elements of H back, like the entire set?
Oh, yeah. So basically, you could show that if you have, say, H1, yeah, that's a very interesting question. And Saif, I would like you to try it out. It's actually not very difficult to show.
Okay.
Yeah, those are the kind of stuff. Sorry?
I came up with that problem when I was doing Lagrange's theorem. That's why I asked.
Oh, yeah, sure. Because the way to prove these things is that to actually assume the opposite. Okay, and you will find that, so, okay, you say that, okay, H1 is, first of all, it cannot be outside the group, right? So it must be inside the group. And you have M elements, so it must be that 2 of them must be equal. That's at least 2 of them are equal, right?
Yeah.
So if that is the case, then if we apply H inverse, then we get H1 is equals to H2, which is a contradiction.
I see. Yeah, that makes sense.
Right. So these are the kind of, this is very simple, but this is not the way we are used to thinking, right? This is the kind of, that's why I want you to do this kind of exercises. Because these are thinking that one is supposed to learn in abstract algebra or some set theory course. And, I never had these courses as a kid, as an undergraduate. So I'm not sure I understand. I have difficulty thinking like that. So, and that's why I'm exposing you and forcing you to do this kind of exercises so that when you, progress in your career, you will have more experience. Okay. So we see that if I pick the element to be from H, then we just get the subgroup back. Okay. So number 2 is that, you can analogously define the right coset as Hg, not Mercury, say H1G, H2G, ... HMG. Okay. So number 3 is that a coset is not necessarily a group. We saw that the trivial coset, EH, that is a group, but the other cosets, need not be a group, okay? All right, so then, I gave you the Lagrange's theorem, and Lagrange's theorem is basically telling you that, so this is the exercise. I learned an interesting fact about Lagrange is that I think his name is Joseph Louis Lagrange, but he was actually born as an Italian. So his original name is Giuseppe Luigi Lagrangia. So yeah, so it got Francofied. So Lagrange's theorem is saying is that suppose we have a finite group G, and then H is a subgroup, then the order of H divides the order of G. That is, K is a positive non-zero integer. Okay? So this is Lagrange's theorem. So if G is a finite group, if the order, so one of the comments you can make is if G is a finite group whose order is a prime number, then it has no proper subgroup, right? Because otherwise, there would be a, it would divide, there would exist a K. Okay, so the other thing I wanted to say about Lagrange's theorem, and this is kind of if you follow the proof, what you will see is that, the proof consists of dividing, G into disjoint, subsets. Okay? And these disjoint subsets are going to be cosets. H, say G1, H, G2, H, dot, 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 G, K minus 1, H, where K is that integer. And so you will see that this is the case. So, so it's consists of, dividing G into disjoint subsets, which are all cosets. And then G is the union of this. Of these cosets. Okay. And this is related to the next fact. The next fact is that cosets, divide a group into equivalence classes. Okay. So what does it mean? That means that if we have two elements, say A and B, which are both in G, then they are, I would say, coset equivalent. From the context, we know that we are thinking about the coset. There are other equivalence classes, which we will talk about. If, okay, they're coset equivalent, we write this as A is equivalent to B if A can be written as B times H, right? You agree with this? Sorry, B times, let's just rewrite this, say B times H for some H in big H, right? Do you agree? Because that means they're in the same coset, A and B, right? So there's a lot of silence. So I mean, I think there should be some pictures will help. So suppose this is our group. And this is, say, the subgroup. And just color it in a little bit to make it pretty. Okay. And this is H. Okay, so, and so suppose that we have some, say, B here, and we have some A here. And so when we multiply all the elements of H by B, we produce a new set, right? Let me just put this a bit. We produce a new set. And that set is something different from H. Okay? So, you know, this is the new set that we produce by applying B to each element in H, right? And so it could be that in that set includes A. If that is the case, then we say that A and B are in the same coset and that they are equivalent. They're equivalent, they're coset equivalent, okay? Do you understand the definition and the picture, set theoretic picture?
Yes, sir, understood the picture.
Anyone else has questions or comments? Or, I mean, these are a bit abstract, right? So, you know, they're...
Sir,
Yeah.
disjoint.
No, go on.
ডিসজয়েন্ট সাবসেটে ভাগ করতে পারলে পারার কারণে কি হচ্ছে আমাদের ইকুইভ্যালেন্স ক্লাসগুলো আসতেছে?
Exactly. Well, you know, equivalence class, if you can have equivalence classes, if you have any set and there is an equivalence class on that set, then that equivalence class will necessarily divide that set into disjoint sets, okay? That's a theorem from abstract algebra, okay?
Sir, how are we concluding that, you know, A will belong in the same set when, you know, like B is multiplied with each elements of H?
No, we are assuming.
Oh, assuming.
Yeah, if you assume that, then A and B are in the same coset, right?
Right.
If they're in the same coset, then, you know, then this is going to be true. There's going to be some H such that when B multiplies H, we get A. So how, you know, there's another element E, right? And that element is the one which will, when B multiplies E, it just gives back B. But there's some other element, say, H, such that when B multiplies H, it gives you A.
Right, sir.
So this is
Right,
by assumption.
So A equivalence B means they are in the same coset.
Exactly. So this equation, we are saying if this equation is satisfied, we say that they are coset equivalent.
So would you scroll up a bit on the Lagrange's theorem part? So this horizontal bar, what does this mean?
This means, so this is a number, this is a number, a whole number. So this means this number divides this number, meaning this number is divisible by this number. Okay? So if this is some integer m and this is n, that means that m divides n.
Okay, got it.
Okay?